Hello students, I hope you are fit and fine. This is plus 2 class chemistry video lesson and we are continuing the study of chapter General Principles and Processes of Isolation of Elements. To make clear the use of Ellingham diagrams in pyrometallurgy, in this chapter we will study about the extraction of iron, copper and zinc from their respective oxides. And in this video we will study about the extraction of iron from oxide ores. The chief ores of iron are hematite, which is the red oxide of iron, limonite, which is the hydrated oxide of iron, magnetite, which is the magnetic oxide of iron, siderite or spathic ore, and iron pyrites. Iron is usually extracted from the oxide ore hematite. Let us now study the steps involved in the extraction of iron from its ore one by one. Firstly, the ore is crushed with jaw crushers, and the crushed ore is then concentrated by gravity separation process, in which the crushed ore is washed in a stream of water when lighter sand and clay particles are washed away, while the heavier ore particles settle down. In case of the sulfide ore, that is iron pyrites, the concentration is carried out by froth flotation process. After this, the concentrated ore is calcined, means it is heated strongly in the presence of a limited supply of air in a reverberatory furnace. During calcination, the moisture of ore is removed. The impurities of sulfur, phosphorus, and arsenic escape as their volatile oxides. Ferrous oxide is oxidized to ferric oxide, thereby preventing the loss of iron as slag during smelting. The ore becomes porous and hence is more suitable for reduction to metallic state. In case of siderite, which is carbonate ore of iron, ferric oxide is formed during calcination. And in case of sulfide ore, that is iron pyrites, conversion to oxide is carried out by roasting. Means the concentrated ore is heated in the presence of excess of air. Then the calcined or roasted ore is reduced with carbon. That is, it is smelted in a blast furnace. Blast furnace is a tall cylindrical furnace made of steel and lined inside with fire bricks. It is 25 to 60 meter high and 8 to 10 meter in diameter at its widest part. At the top, the furnace is provided with a double cup and cone arrangement, which helps to feed the charge from the top without letting any gases from inside to escape. The charge is fed to the cup, and when it is full, the cone is depressed so that the charge automatically goes down into the furnace, and subsequently the throat of the furnace is automatically closed. Near the top, furnace is also provided with an outlet for waste gases. At the base, the furnace is provided with small pipes called turries, through which a blast of hot air is admitted. There is also a large crucible at the lowest part to hold the molten metal. It is provided with two holes. One is a tapping hole for withdrawing molten iron, and one is a slag hole for withdrawing slag. The charge consisting of calcined ore, coke, and limestone is introduced into the furnace from the top through cup and cone arrangement. At the same time, a blast of hot air preheated to about 1000 Kelvin is blown into the furnace through turries. The coke is added in charge to serve both as a fuel as well as a reducing agent, while the limestone present in the charge acts as the basic flux. The temperature near the top of the furnace is around 523 Kelvin, while it is around 2170 Kelvin near the bottom. It is thermodynamics which helps us in understanding how coke reduces iron oxide to iron. In fact, iron oxide is reduced to iron mainly by carbon monoxide, but some reduction by carbon also takes place. So one of the main reactions involved in the reduction process is FeO plus C gives Fe plus Co. This redox reaction can be divided into two half reactions. One is reduction half reaction and the other is oxidation half reaction. In the first reaction, iron oxide is reduced to iron. Let the change in Gibbs free energy for this reaction be delta G FeO Fe. In the second reaction, carbon is oxidized to carbon monoxide. Let the change in Gibbs free energy for this reaction be delta G CCO. When these two reactions are coupled to give the redox reaction, the net Gibbs free energy change will become equal to delta G FeO Fe plus delta G CCO. The resultant reaction, that is equation 1, will take place only if change in Gibbs free energy for the reaction is negative. We can find the approximate temperature for the reduction of iron oxide to iron with the help of Ellingham diagram. At approximately 1073 Kelvin or above, the carbon to carbon monoxide line is much below the iron to iron oxide line. This means that delta G for iron to iron oxide is larger than delta G for carbon to carbon monoxide, and hence the change in Gibbs free energy for the reaction is negative. So we can say that at 1073 Kelvin or above, coke will reduce ferrous oxide to iron and itself will be oxidized to carbon monoxide. In contrast, at temperatures below 1073 Kelvin, the carbon monoxide to carbon dioxide line lies below iron to iron oxide line. Therefore, below 1073 Kelvin, carbon monoxide can reduce the oxides of iron, that is Fe2O3, Fe3O4, etc. Therefore, in the blast furnace, reduction of iron oxides takes place at different temperatures. Now let us discuss the various reactions taking place in the furnace at different temperatures. Firstly, we have the zone of combustion. Here, near the Turies, coke burns to form carbon dioxide. This reaction is exothermic, which produces a lot of heat, and the temperature here rises to around 2170 Kelvin. Next is zone of heat absorption. This is the lower part of the furnace and the temperature here is between 1423 to 1673 Kelvin. As the carbon dioxide formed near the Turies moves up, it meets the descending charge. The coke present in the charge reduces carbon dioxide to carbon monoxide. This reaction is endothermic, due to which the temperature decreases to about 1423 Kelvin. Then there is a zone of slag formation, which is the middle part of the furnace. The temperature here is around 1123 Kelvin. In this area, limestone decomposes to form calcium oxide and carbon dioxide. The calcium oxide thus formed acts as a flux and combines with silica that can be present as an impurity to form fusible calcium silicate slag. The zone of reduction is the upper part of the furnace. The temperature here is between 500 to 900 Kelvin. In this zone, the ores are reduced to iron oxide by carbon monoxide as shown in these reactions. The further reduction of iron oxide to iron by carbon monoxide occurs around 1123 Kelvin. At temperature around 1123 Kelvin, iron oxide reacts with carbon monoxide to form iron and carbon dioxide gas. The direct reduction of iron ores such as hematite, magnetite, etc., which are left unreduced around 873 Kelvin, occurs completely to iron by carbon above 1123 Kelvin. The lower part of the furnace is the zone of fusion, where the temperature is in between 1423 to 1673 Kelvin. In this region, spongy iron melts and dissolves some carbon, sulfur, phosphorus, silicon, manganese, etc. Sulfur, phosphorus, and silicon are produced from sulfates, phosphates, and silicates respectively, which may be present in the ore by reduction with carbon. Calcium silicate slag also melts in this region. Both the molten slag and the molten iron trickle down into the earth where they form two separate layers. The molten calcium silicate slag being lighter forms the upper layer, while the molten iron being heavier forms the lower layer. These two liquids are periodically tapped off from the two holes provided in the hearth. The iron thus obtained from the furnace contains 2 to 5% carbon and many impurities such as sulfur, phosphorus, silicon, manganese in smaller amount. This is called pig iron. Pig iron is cast into variety of shapes. Cast iron is different from pig iron and is made by melting pig iron with scrap iron and coke using hot air blast. It has slightly lower carbon content and is extremely hard and brittle.